Good morning. Today we're going to be dealing with the real foundational issues here. One of the problems you get into with something like science and mathematics is you make some progress and you think that that's it, but it could very well be that by making additional progress, you end up revisiting everything you've already done and then some to try and sort it all out. And that's what we'll be doing today. So just bear with me. We're going to jump into this right now and we'll see where things go. Here's the show. We've called this Foundations, Philosophy, and Metamathematics. Our belief here is that it's mathematics, not physics, that's the fundamental glue that holds everything together. That's the collective unconsciousness all around us. So we've got something here from Stephen Wolfram, where he deals with the topic of metamathematics, an approach toward showing that algorithms can explain what we would call as physics today. And if you can explain physics, you should be able to explain chemistry and biology as well. So that's one side of things. Another side over here is we've got what's called epistemology, which has a slight overlap with metaphysics, and ontology, which is contained within metaphysics. And we're going to argue that metamathematics encompasses all of this. It's a foundational issue. The foundation is shown here. Here's the foundation. And finally, we close with Rodin, the thinker. So with that, let's jump into it. Okay, metamathematics, metaphysics. This is the branch of philosophy that deals in the deep scaffolding of the world, the nature of space, time, causation, existence, the foundation's reality itself. So this is generally considered untestable since the assumptions underlie all our efforts to conduct tests and interpret results, and those assumptions go unspoken. So we for example, deal with Newton. Newton viewed space as having three dimensions, width, length, and breadth. And then there was time, and time ran on. Time was separate from space, so be it. Then we get into the 19th century, early 20th century, when it becomes clear that it's really space-time. Space and time are linked in some intrinsic way, that time apparently is another dimension, but it's in some sense perpendicular to the other three. And this led to space-time, which is the foundations of special relativity. Even that is going to be revisited as we'll get into this. So the thing to keep in mind here is most of the time, this is okay, this is fine. The intuitions we have about the way the world works rarely conflict with our everyday experience, as long as we stay away from speeds approaching the speed of light or scales that are far beyond atomic or quantum scales. We can assume that objects have features, that we can measure them, that we share this in these dimensions, and that works for all of us. So as long as this philosophy works, it lurks undetected in the background, and it leads us mistakenly to believe that science is something that's separable from metaphysics. However, and this is where it gets interesting, where we have the uncharted edges of experience, where you run at speeds approaching the speed of light and scales that are down in the size of the atom or fractions of an atom, the quarks and subquarks that are there. Those intuitions cease to really be useful to serve us. They make it impossible for us to do science without confronting these assumptions head on, and we're in a place which can no longer be neatly distinguished. The physicist Eric Cavalcanti calls this experimental metaphysics. You can call it what you want, but it's the edge, it's the envelope. So he's carrying this torch of a tradition that goes back to a long period of time, and ends up dealing with the tools of science to test our actual worldviews. Cavalcanti is native of Brazil. He's a professor in the faculty of Griffith University in Brisbane, Australia. And he and his colleagues have published the strongest result attained in this area called experimental physics, which is a theorem that places strict and surprising constraints on the nature of reality. And now they're designing experiments to test this. The injection of philosophy into science to test something many scientists view as really not scientific. In some sense, the knowledge we obtain through experimental metaphysics is more secure and more scientific because it vets not only the hypotheses of science, but the premises that usually lie hidden underneath. So the dividing line between science and philosophy has never been clear. It's often drawn along testability. Any science that deserves its name is said to be vulnerable to tests that can falsify it. That's why we are always testing the limits of science to see where it breaks down, and that leads us to extending those limits. But what we're dealing with here is the breaking down of the limits is at a fundamental level, and we might have to reshuffle the entire deck, see what's going on. So, for example, the idea of dark matter and dark energy leads us to deal with 95% of the universe is made up of dark matter and dark energy. We've been dealing with matter and energy for 500 years in Western science that basically encompasses 5% of the universe. Well, if there are 3 spatial dimensions for that, then 3 dimensions holds 5%, or 60 dimensions holds all of it. Well, where are these other dimensions? This is an example of something where there's a breakdown of what's fundamental here. And in fact, what's amazing is the fact we can say anything at all about this, and it appears that 24 spatial dimensions make up the universe, but in a very highly structured way, not at all obvious. So the thing to keep in mind here is that physicists believe they can do real science, and the philosophers are in their armchairs, stroking their chins, puffing on their pipes, stroking their beards, but get out of the way. The physicists are really the people doing the heavy lifting. And what we're going to argue here is that's not the case at all. The first thing we're going to deal with is the testability distinction. So philosophers have long known it's impossible to prove a hypothesis. No matter how many white swans you see, the next white swan could be a black swan. So that's why Karl Popper, who's shown here, got a bunch of pictures here, let me get out of the way, famously said a statement is only scientific if it's falsifiable. If we can't prove it, we can at least try to disprove it. And that's great. The 1906, the French physicist Pierre Duhem showed falsifying a single hypothesis is impossible. Every piece of science is bound up in a tangled mesh of assumptions, and these assumptions are about everything, from underlying physical laws to the working of specific measurement devices. So if the result of your experiment proves to disprove your hypothesis, you can always account for the data by tweaking one of your assumptions while leaving your hypothesis intact. And so it goes. Take, for instance, the geometry of space-time. Immanuel Kant declared that the properties of space and time are not empirical questions. He thought not only the geometry of space wasn't necessarily Euclidean, meaning that a triangle's interior angles add up to 180 degrees, So as an example, if we had a triangle on a sphere, say a triangle going from the North Pole down to the one line down to the equator, and then going along the equator a bit and then back up to the North Pole, we'd see that the angles of that add up to like 270 degrees. We can make 3 right angles in a triangle on a sphere. That's not a Euclidean geometry. But this fact had to be the basis for any future metaphysics. So this is not something that's testable because it provided the very framework within we understand how our tests work in the first place. But in 1919, astronomers measured the path of starlight as it got bent by the gravitational influence of the sun, and they discovered that the geometry of space itself wasn't Euclidean. It was warped by gravity, as Einstein had predicted. Or did they? The French polymath Henri Poincaré, an incredible mathematician, offered up an intriguing thought experiment. Imagine the universe as a giant disk that conforms to Euclidean geometry, but whose physical laws include the following. The disk is hottest in the middle, coldest at the edge. The temperature falls proportional to the square of the distance from the center. And this universe features a refractive index, which is a measure of how light rays bend, that is inversely proportional to the temperature. So in such a universe, the rulers and yardsticks would never be straight. Solid objects would expand and shrink with the temperature gradient, while the refractive index would make light rays appear to travel in curves rather than straight lines. So any attempt to measure the geometry of space, say by adding up the angles of the triangle, would lead one to believe the space was non-Euclidean, but it isn't. It is what it is. So let's go on with this. Any test of geometry requires you to assume certain laws of physics, while any test of those laws of physics requires you to assume the geometry. So the disk's world, the physical laws seem ad hoc here, but so are Euclid's axioms. Poincaré is right, in my opinion, said Einstein in a 1921 letter. Only the sum of geometry and physical laws is subject to experimental verification. And this is what we'll harp on here repeatedly, is the underlying geometry influences the physical laws and vice versa. They're just intrinsically linked. There was an American logician, Willard Quine, is shown down here, where the unit of empirical significance, the thing that's actually testable, is the whole of science. So the simplest observation, say that the sky is blue or the particle is positioned here, forces us to question everything that we know about the workings of the universe. This is what foundational questions are all about, is going back to really what is going on here. It's actually worse than that. We've got a 20th century Swiss mathematician, Ferdinand Gonseath, shown here. Gonseath said that science and metaphysics are always in conversation with one another. Metaphysics provides the foundations on which science operates. Science provides evidence that forces metaphysics to revise those foundations, and the two together adapt and change like a living, breathing organism. So science and philosophy together form a single whole. They're not separate. So with the two tied together in a Gordian knot, we might be tempted to throw our hands up. We can't put scientific statements to the test without dragging out metaphysical statements along them, but there's the flip side. It means metaphysics is testable, and that's why Cavalcanti, who is working there in this area, doesn't refer to himself as a physicist or as a philosopher, but he says he's an experimental metaphysicist. So he decided to pursue a doctorate in quantum foundations, and by miracle of miracles found a job in Australia. And his dissertation begins: to understand the source of the conflicts of quantum foundations, it's essential to know where and how our classical models and intuitions start to fail to describe a quantum world. This is the subject of experimental metaphysics. The professor on his thesis committee put down the thesis at that point and said, "This isn't physics." In other words, I don't believe anything you're saying here from this point on. However, He was not deterred. He made the case that the line between physics and philosophy had already been blurred beyond repair. A Northern Irish physicist, John Stuart Bell, shown up here, had encountered a culture of physics that had no patience for philosophy. We had Einstein and Bohr arguing over the nature of reality, how you could have waves being particles and particles being waves. What does it mean to be a particle or be a wave when they appear to be intrinsically blurred between one another? And the physicists, were not willing to spend a lot of time on this. They just wanted to get on with physics, ignore this sort of thing. Let's go for it. But John Stuart Bell, discovered a new possibility. While it's true you can't test a single hypothesis in isolation, you can take multiple assumptions and see if they stand or fall together. So this is non-trivial. Let's take a look at this. Those assumptions are typically understood to be locality, the belief that things can influence each other instantaneously across space. This is why physicists come up with the notion of a field, that the field can propagate through space, energy of some sort, but it propagates at a finite speed, and therefore this locality governs how things behave. But then there's realism, that there's some way that things simply are independent of their being measured. So Bell came up with a theorem, not surprisingly called Bell's inequality, for any theory operating under the assumptions of locality and realism. There's an upper limit on how correlated certain events can be. However, quantum mechanics predicted correlations that broke through that upper limit. In quantum mechanics, it's possible to entangle two entities and separate them arbitrarily far apart, millions of light years. When I change one of them, it instantaneously changes the one that's millions of light years away. So the notion of locality is gone. People then decided to try and figure out how to test this theorem. They tried to rewrite it in a different way, did all kinds of things, and came up with a test to measure correlations between pairs of photons. And the results show that the world bore out the predictions of quantum mechanics, that the correlations were far stronger than Bell's inequality allowed. And this meant that locality and realism can't both be features of reality, through which the two we ought to abandon. The experiment, which of these do we abandon? Well, we don't know. In fact, it might be that there's a completely different point of view that we have to adopt here, which shows how little we really know, or how important it is to be open-minded about trying to sort these things out. Michel Besso, Einstein's best friend and sounding board, was the only person who credited Einstein with helping him come up with the theory of relativity. But Besso helped less with the physics than with the philosophy. Einstein had always been a realist, believing in a reality behind the scenes, independent of our observations. But Besso introduced him to the philosophy of Ernst Mach, who argued that a theory should only refer to measurable quantities. So Mach, by way of Besso, encouraged Einstein to give up his metaphysical notions of absolute space and time and motion, and the end result was the special theory of relativity. When Einstein published this in 1905, physicists weren't sure whether this was physics or philosophy. Others had written down these equations, but it was the interpretation of the metaphysics behind them that was new. But the metaphysics was enough to lead to new science. Special relativity gave way to general relativity, a new theory of gravity, along with new testable predictions. And Besso later befriended Gansev in Switzerland. The two took long walks together. Gansev argued that physics could never be placed on firm foundations, since experiments can always overturn the most bedrock assumptions in what it's built. So in a letter which Gansev published in a 1948 issue of the journal Dialectica, Besso suggested Gansev refer to his work as experimental metaphysics, which is where Cavalcanti got it from. There was a founding of an association in Bienne, Switzerland. Science and philosophy form one body, and all that happens in science may resound on philosophy, even its most fundamental principles. This was a radical statement, shocking to both science and philosophy. And there was an underground newsletter called Epistemological Letters, a kind of physics zine, magazine with typed mimeograph pages speckled with hand-drawn equations, mailed out to 100 or so physicists and philosophers. For a new counterculture, the daring few wanted to discuss experimental metaphysics. Bell's theorem was always at the center of those discussions because previous work in physics let its metaphysics go unacknowledged. In Bell's work, the two were truly and explicitly inseparable. The theorem was not about any particular theory of physics. So this is what physicists call a no-go theorem, a general proof showing that any theory operating under the metaphysical assumptions of locality and realism cannot describe the world we live in. You want a world that is just some particular way, even when it's not being measured? You want locality? No go. Or as Shimoni put it in the letters, in a play on Bell's name, those who want to hold such a worldview should remember the sermon to John Donne, and therefore never send to know for whom the bell tolls. It tolls for thee. A little cute way to frame things. So Bell was both a philosopher of physics and a physicist, and in some of his best papers, he basically combined the two, which of course rattled the editors and the physicists that are the gatekeepers of science. This kind of work was definitely not seen as respectable. The French physicist Alain Aspect went to Bell and suggested a new experiment to test his inequality. The worry was that in doing the experiment, that would kill my career, which is a real concern. And so we end. To be continued in further talks. Thank you very much and enjoy.